Welcome to the lectures on evolution of air interface towards 5G. So, we have seen the frame structure for the 5th generation mobile communication system, especially the series which comes from the house of 3GPP, and we were discussing how the slot size remains constant in terms of number of OFDM symbol, but when it comes to the time duration for the slot, it changes because the OFDM symbol changes. So, the entire frame structure now becomes flexible with different amounts of resources available for different services. And as a result of which, what we see over here is a combination of several different services which could be multiplexed together to provide various different services over the same air interface. Now, this is very important, which has happened over the earlier generation system, which did not provide such kind of flexibilities. And we have identified that for example, in this case the URLLC, which is the ultra reliable low latency, especially we will talk about the low latency part, which becomes very critical. So, in a typical communication system, a slot is the unit which gets addressed. So, in the earlier generation there was a subframe which was getting addressed 1 millisecond duration. Now, you can address a slot, that is point number 1, but look at the flow of things when it goes from Tx to Rx. An entire transmission unit has to be decoded at the receiver. So, it has to be generated at the transmitter, going from transmitter to receiver through propagation. Okay. At the receiver it has to be decoded and then it has to be sent back to the transmitter. Right. So, the basic unit which constrains this entire flow is this unit, which is the slot unit, which is now addressable. Earlier it was a subframe unit, plus there is this processing delay at the receiver side as well as at the transmitter side. Now, why we are talking about this round trip? Because there is constraint on latency on the round trip. If this duration is 1 millisecond, then there is by no means by which one should be able to respond within 1 millisecond from one node to another node with the shortest possible internode connection. However, the only way one can do it is to reduce this duration. So, first and foremost, with mu equals to 0, what we find that this duration becomes 1 millisecond, the duration of a subframe, which is the one for the 4th generation system. But here with different mu configurations, one can change this slot duration to a much smaller value. And you have seen in the previous lecture that the subframe size remains constant, but the OFDM symbol duration can become very small. So, there is another mode where it can become even smaller than this. So, when it becomes even smaller, that means the symbol duration becomes around 4.5 microsecond, including the cyclic prefix, roughly speaking, that is the value. So, that means if we take 14 OFDM symbols in one slot, then the number is not very high, right? It is within around 70 microseconds and so on. So, that means you have a huge amount of time. So, if this particular duration is within 100 microseconds, let us say, so that means one should be able to do a round trip transmission if this is, let us say, less than 100 microseconds. So, then you have 10 such slots available for transmission. So, that means there is sufficient interval in terms of slot count that can be used, and hence one should be able to transmit the slot. The propagation delay is not much if the distance between the transmitter and receiver is small. If the packet duration is small, then the decoding time would also be small, and hence it will help respond to a total of 1 millisecond of response time. Further, we will also see that when we go to this new generation system, there is a provision for mini slot compared to only subframe or the slot duration for mu equals to 0, which can also be addressed. And these slots, mini slots, can be of 7, 4 or 2 OFDM symbols, meaning that within a very short burst, one can say this is the entire transmission unit. So, if the burst is short, decoding time is also short, response time becomes short, because the total response time is counted in terms of multiples of this transmission time. okay, of a slot, of a particular slot. So, this smallest slot duration can provide you a lot of flexibility and capability towards meeting this URLLC. So, what we see is that because there was a requirement to support such things, such different services, this particular flexible structure can provide a lot of support towards meeting the multiple different services within one particular frame structure. Now, we move on to understand the numerology even in a better sense or complete the understanding. One has to go for 38.104, that is the next part, which talks about the base station radio transmission and reception. So, in that there are two sets of frequency ranges that are defined. Frequency range 1 is from 450 megahertz to 6 gigahertz, and the next one is from 24 gigahertz to 52 gigahertz. So, that means there is two different ranges over which things are going to happen. So, usually this is referred to as less than 6 gigahertz and the other set which is greater than 6 gigahertz frequency. Okay. So, we also have 38.101. So, if we take out one particular statement from that, what we find is that the UE channel bandwidth supports a single NR RF carrier. NR is new radio frequency carrier in the uplink or downlink at the UE. That is one part. From the BS perspective, different UE channel bandwidths may be supported within the same spectrum for transmission to and receiving from UEs connected to the base station. So, what it effectively means is that different user equipments will be connected to the base stations and different UE channel bandwidths should be supported. So, not only that, since each UE can choose a different numerology, the base station may be simultaneously supporting different numerologies together, and one would encounter a situation where one is going towards a mixed numerology. So, we will see the particular structure, how it fits in. The base station should be able to support multiple users within the same spectrum. So, that is what it means. It also means that each UE with different configuration of maximum channel bandwidth leading to different subcarrier spacing, right. In other words, within one carrier bandwidth from the base station's perspective, multiple UE subcarrier spacing is possible. So, what we conclude overall is that UEs can have different subcarrier spacing and different UEs can have different subcarrier spacing, while the base station must support them even if they are within the same spectrum. So, that is what we get. So, overall picture that we get is in standard LTE, this is the kind of figure which we have referred to earlier and which we will see where the subcarrier spacing is constant. But now, under mixed numerology situation, so we have the mixed numerology mentioned over here, different subcarrier spacings should be supportable from the base station. So, this is a very different thing compared to what has been encountered in the earlier generation system, and this would lead to many different questions and many different issues, many different aspects. So, we will get into the discussion of that particular aspect. So, let us look into that. So, we will now discuss about what is the genesis and how things have come. So, primarily I would like to point out over here that this particular work that we are referring to is not a very new work. It actually started at least 10 years from now. So, in the year around 2004, 2005, we will find that there is reference for these works. 2004, 2005, we will point out such references, and one such reference that we will talk about is one particular material which will actually give the details about it later on. So, let us get into how things are and why things are in that format. So, we have seen this particular picture earlier where we said that between the transmitter and the receiver there are multiple paths. So, multiple paths would give rise to a channel impulse response as depicted in this particular picture, and we said that there needs to be a guard interval or TCP which should be greater than the tau max. So, this is the tau max of the channel, correct. Along with this, there is also mobility which gives rise to Doppler. Okay. So, there we would find that in a particular situation you will be having different Doppler conditions coexisting. If different Doppler conditions coexist, then each of the users would going to experience a different kind of channel. So, mobility gives rise to Doppler, user distance gives rise to path loss, and user equipment capability gives rise to various ICI problems, various ICI capability. Further, what we have seen in the earlier discussion is that there are different frequency ranges of operation. So, if one thinks of below 6 gigahertz and the another set above 6 gigahertz, these different frequencies, if we look at the components or devices that would be useful to making them, as you increase and go towards higher and higher frequency, one of the important factors that comes into play is phase noise. The effect of phase noise becomes larger. Phase noise effectively means that the oscillator frequency that is generated is varying about Fc, if this is the Fc, beyond just being a delta function. So, in the frequency domain it is no longer a delta function, rather in frequency domain you will find that there is a certain amount of spread in the frequency and there are certain other spurious frequencies that also come in. So, as you increase the carrier frequency, this particular effect dominates. Further, as you increase Doppler, what we find is that the Doppler frequency Fd is proportional to the velocity of the vehicle multiplied by the carrier frequency. So, simply if the velocity increases, then Doppler frequency increases, or if the carrier frequency increases, Doppler frequency also increases further. So, if we go from the 4G to 5G, first and foremost the maximum frequency supported increases from 350 kilometers per hour to 500 kilometers per hour, and the frequency of operation not only goes up to 6 gigahertz, but it also goes beyond 6 gigahertz. So, overall these conditions indicate that your Doppler frequency, Doppler experienced increases, also the phase noise increases, but at the same time you will find that stationary users would also be there, that means pedestrian users would also be there. There would be indoor conditions, there will be multitude of various outdoor conditions which needs to coexist at the same time. So, if we look at what is the effect of Doppler, so or let us say phase noise or carrier frequency offset. So, we said that in OFDM the subcarrier spacings are such that they are orthogonal, that means the peak of the desired carrier coincides with the null of all other carriers, that means there is no interference. But if there is shift in carrier, the desired signal strength reduces and there is huge amount of interference that comes into play. Okay. So, if this interference comes into play, there is heavy reduction of signal to interference ratio. If you have Doppler, then the problem is there is no one single frequency shift. So, if we call it a shift, then it can be handled, that means one can track the frequency offset, one can do it. But because of multipath, this shift does not happen, and instead what you get is basically a Doppler spread condition. Right. So, what is depicted in this picture is this power spectral density versus frequency, and we see one particular spectrum which imitates the Jake spectrum. That means there is a whole bunch of frequencies. What it means that the receiver would perceive that there are several such multitude of frequencies which come in, and there is a smearing of the signals in the frequency domain. They just overlap in multiple values. So, in that case the CFO tracking algorithm is not going to be much useful under that situation. If there is only a frequency shift, then that kind of algorithms are useful, right. And if you have complex ICI cancellation algorithms, that would also increase the complexity of the entire system. So, if we look at how does the Doppler affects the intercarrier interference, we will find that in the intercarrier interference power term, this is the power for intercarrier interference, there is a ratio of frequency offset with respect to the subcarrier spacing. So, this delta FSC is the subcarrier spacing. So, what you see, as this numerator increases, the ICI power increases, right. As you increase that, the ICI power increases. So, one way which we as designers or transmitters can reduce the effect of ICI is by changing the denominator term which is in our control. And as you can clearly see, this denominator term which is delta FSC indicating subcarrier spacing, it can be varied. So, this way one can easily implement a method by which one can take care of such Doppler spreads, and this exactly has been adopted in the 5th generation system, and originally it was proposed in the by the name of adaptive subcarrier bandwidth by us when we were working on this particular issue way back in 2004, 2005, and as well as we have proposed various mechanisms to handle this in the subsequent years. So, we will get into all the details of how this kind of thing works. So, going further, we just look at this, how does this pictorially represent. So, typically because of frequency offset, one gets a reduction in signal strength as well as increase in interference values, but then this particular variation is delta f, that is a small delta f, and this is the capital delta f. So, as you increase the subcarrier spacing, simply you can improve the signal condition at the receiver. So, these indexes indicate the desired and interference terms, and thereby you can improve the overall condition. So, what you get is that as you keep increasing the subcarrier spacing in this axis, and these different curves are for different mobility conditions that we had tested long time back. We are not introducing a newer set of values, because this is an earlier work that we had done. So, what you see is that at 10 kilometers per hour, you get a certain signal to interference ratio. As your Doppler increases at a particular value of subcarrier spacing, your signal to interference ratio becomes smaller and smaller. This is something very critical to note simply by virtue of this particular case. As you increase the subcarrier spacing, the signal to interference ratio increases beautifully, especially for the ones where you have higher Doppler condition, right. So, this clearly indicates that to handle higher Doppler conditions, having a higher subcarrier bandwidth is a much better solution than implementing advanced interference cancellations techniques, which also get limited when you have multiple paths coming into play and there is a spread. So, with this we have discussed that we have also analyzed the throughput condition, that means when you increase the subcarrier bandwidth, what happens for different throughput conditions. What we find is that as you increase the subcarrier bandwidth or as you decrease the subcarrier bandwidth, we have discussed this when we are talking about the frame structure. For longer OFDM symbol durations, the guard interval duration is also longer. Sorry, I mean guard interval duration is correspondingly longer. Now, if you have a certain channel impulse response and you cannot do much with the guard interval part, that means you are restricted, then the overall system efficiency decreases, right. So, that is what we find, that if you are maintaining a certain subcarrier spacing and you are changing and you are simply studying the effect on of different mobility conditions, we will find that the throughput would decrease as one increases the subcarrier spacing, but one maintains a certain mobility conditions. Okay. Whereas, in another situation it initially increases, then more or less it remains the same up to a certain point. So, we go beyond this and we look at the overall structure. So, here what we have plotted is on the x axis we have given the velocity, okay, and higher number of subcarriers or reverse, lower number of subcarriers indicate higher subcarrier bandwidth, because you have a bandwidth divided by n. So, as n increases, delta f decreases or vice versa. So, as n decreases, delta f increases, right. So, 2048 has a certain value of delta f with 20 megahertz bandwidth. As we increase to 1024, the delta f increases. As we go to 512, delta f increases further. So, what we see is being depicted in this particular picture is that if you are maintaining a certain narrow subcarrier bandwidth, this is very critical, the throughput decreases heavily with increase in mobility, right. After a certain point, you simply cannot support the throughput because your interference is very high. If you are using a little bit wider, then you can support a higher throughput, but there is a decrease in throughput for low mobility conditions. Similarly, if we increase the subcarrier spacing further, we find that the throughput has improved in higher mobility conditions, but it has decreased in the low mobility condition. As we go on increasing, so this green set is for 256, which is several times wider than the 2048, just remember this. So, this directly corresponds to the new name of numerology that we are using for 5th generation, but the original name that was proposed was adaptive subcarrier bandwidth. So, what we have shown is these different shaded portions indicate the range of mobility which causes a certain Doppler, which can also be connected with corresponding phase noise in terms of delta f, which gives the highest throughput. So, if we clear these things up, so we will find that each particular section represents the corresponding throughput for that subcarrier spacing. So, if we have this delta f mu, this delta f mu is much larger than delta f of 2048, and hence it can support a larger throughput over here, but there is a significant reduction in the throughput in the lower mobility condition. So, what is suggested or proposed is that one can adaptively change the bandwidth of the subcarrier, and depending upon the mobility condition or channel condition, one can flexibly allocate the subcarrier spacing, thereby one can get the best throughput under all conditions of subcarrier spacing or phase noise or whatever is the situation. So, if we look at the structure, what we had proposed is we had considered that let us say there would be a much wider bandwidth. In that case, one would limit a sub part of the bandwidth to let us say 20 megahertz, because as you increase the bandwidth, your processing complexity also increases. So, we had assumed that let there be smaller parts, and smaller parts can be of various bandwidths depending upon the particular realization. So, this is in frequency domain. You can have several chunks which run in parallel. One could also think of doing this in TDM fashion depending upon the implementation. Technically it is feasible, but this is the approach which is now adopted in the 5th generation system, and the picture that would look like is in a standard LTE, this would look like this. In a variable subcarrier bandwidth, we have certain fractions having narrow bandwidth, certain fractions having wider bandwidth. This work that we are representing over here is an extreme case of the picture over here. In this case, we had a group of subcarriers which are next to each other, whereas in this case we have allocated a consecutive group of subcarriers who have a wider subcarrier spacing. Let us say this is 2 and this is delta f SC1, we have delta f SC2 greater than delta f SC1, right. Whereas, we can think of an extreme multiplexing of things where we will find that different bandwidths are multiplexed simultaneously, and correspondingly the different time domain pulses would also exist simultaneously. So, what we see is that the narrow band subcarriers have a longer pulse duration and the wider band subcarriers have a shorter pulse duration, So, with this also the detailed analysis of signal to interference plus ratio, noise ratio and the throughput calculations have been done, and as I had shown earlier, this particular reference which we will give you in details, including the cover page which contains this particular image, one can find all details about the performance analysis that one needs to do. So, here we have also proposed the structure in which this can be worked out. That means, one can think of different FFT sizes, that means they are all operating on the same bandwidth, but the subcarrier spacing is simply different. So, that means, if the total bandwidth is B, subcarrier spacing 1 should be equal to B divided by N1, and this subcarrier spacing 2 is the same bandwidth divided by N2. So, in this case N2 is less than N1, leading to delta FSC greater than delta FSC1, and here what we indicate is that in one set of FFT IFFT operations, one would activate a few subcarriers, that means send them non-zero signals with xk not equal to 0, and it would let the other subcarriers having xk equal to 0, while in the other FFT one can have the xk's not equal to 0 in the portion which is not overlapping in the frequency domain of the other system, whereas here you can have xk equals to 0, xk are the constellation points. So, by virtue of which, if we look at the final frequency domain picture, we will find that these subcarriers are present because of this. In the next portion we will find wider subcarriers present because of this. So, here we will find wider subcarrier spacing, here we will find narrower subcarrier spacing. So, implementing this is also not a problem, and this particular picture generalizes the entire thing, where we can have different subcarrier spacing. So, this you can connect to different numerologies, okay, and it can be decoded by different receivers simultaneously. So, as if this is the base station and these are the different receivers as have been indicated here, receiver 1, receiver 2, receiver 3, they can decode independently, and one can also think of a reverse direction transmission. That means, each this becomes now transmitter would activate only these few subcarriers out of the entire set of subcarriers. This transmitter would activate only this set of subcarriers. So, when the signal arrives at the base station, one would find that corresponding to this there is some narrow band subcarriers, then there will be a little bit wider band subcarriers, and there will be even wider band subcarriers next to each other. So, then this way one can have a mixed numerology architecture. In this figure we have given a detailed block diagram of how the transmitter and receiver would look like. So, this one is the BS or the downlink transmitter. Here we have the uplink receiver structure. So, all these details have been proposed and you can find them in the different material. In this we have verified that the spectral efficiency improvement from 10 to 30% can be had. It can support different mobility conditions and different phase noise conditions, as well as low complexity ICI management can be done. You need not cancel the ISI, right. Only thing you need to do is to dynamically adapt the subcarrier bandwidth, and which you will now term as numerology. The references which we would point out is the first work here, which contains all details of the things that were that are presented in this particular discussion and relevant for the 5th generation air interface, and there are different publications which also point out to the same. This is the earliest work in this particular direction, and you can also refer to a patent which can be easily accessed from this particular website, which gives all details of the adaptive subcarrier spacing. You call it variable subcarrier spacing, or whether you call it numerology as per the new statement. I would also point out at this point that so this particular thesis that you are seeing in front of you, you can also refer to this particular work which describes the hardware realization of such a thing. So, as you can see from the picture which is depicted on top of the particular PhD thesis by Christian Bloom, which is maximizing OFDM performance through real time adaptivity, and you go into the details, you will also find that they have also referred to the work that I just presented to being one of the first kind of work in this domain, and we are all really extremely happy that finally these kind of proposals which we thought is pertinent is finally being used in the 5th generation system, where the terminology that is used is numerology, and we have the most complicated situation which is the mixed numerology, and if you want a detailed analysis of this numerology, please refer to all the details that we have pointed out over here to find detailed analytical expressions, performance analysis, how to do the simulations, and all other details available. So, we stop this particular lecture here. We will continue to discuss some more things related to the choice of cyclic prefix, how does it affect and what are the uses, so that it can also provide you with more tools and methods by which you can improve the systems even beyond what is available today. Also will give you information about the problem that is associated with coupling the cyclic prefix along with the subcarrier spacing. Further, we will go beyond and discuss about the slot aggregation, which is also one of the important characteristics which have been investigated earlier. Thank you.